Okay, so this video is going to be about 6.8, which is about the shadow price and how the shadow price is related to the dual. So just as a reminder, what we were doing last time was the dual theorem, which says that if you have beta, which is, I guess, script B, is an optimal basis, then we can write down the solution, the optimal solution to the dual, right, by taking CB transpose times B inverse. Okay, and then so what we've shown here is that that's a transpose so that we make y into a column vector. That's not really necessary, but just to be consistent. Okay, and then we saw a quick example here. This is our original tableau here, and then here's our final tableau here. And so what we were doing then was we looked to see, well, where is the value of the y's, the solution to the dual, if I have the final tableau. And of course the answer is that the shadow prices were lined up right here, and that's because originally we had these two slack variables right here. Okay, so the slack variable corresponds nicely to these columns of the identity with zeros on the top, and so therefore what we showed notationally, right, is that we get these computations. Good, and so we can double check the value of the dual by computing the value of our z, right? And so the CB transpose in this case is 1, 6, and so therefore we get that z, or I guess this is w now. Let me change to y again. This is w equals 1 times 4/3 plus 6 times 1/3, and that gives us our 10/3. And so that is the same thing as our optimal z value. So z equals w, and from our strong duality we said that we have an optimal solution. Good. Now, what happens when we take a look and check to see how we would compute some sensitivity analysis? And the sensitivity analysis I want to do today is I want to change the right hand side of my tableau and see how that changes the values, right? And so we did this computation last time as well. We said that I'm going to change b to b plus e1, and so this is, I'm just going to change it by 1, right? So do you remember what that was called when we changed the right hand side just by 1? That is called, what we're going to compute is the new z value from which we'll get the shadow price. Okay, so if I change my b, my right hand side, whoops, change too much of it, from b to b plus e1, and then compute the optimal value there, I'm going to take my b inverse times b plus e1, keep going with that computation, b inverse times b plus b inverse times e1. This is your old, or the optimal tableau right hand side here, and this is just the first column of b inverse, right? Good. Now, what happens when we compute our new z value using this right hand side? Z new then is going to be CB transpose, and instead of B inverse it's going to be B inverse B plus B inverse the first column, right? And so if I write that out, I get CB transpose B inverse B plus CB transpose times B inverse 1. And so what is that? Well, this is Z old, right? And this is Y1. Yes, and so the shadow price of constraint 1 is Y1. Very nice. So in this case, in our previous exercise here, we can see that, go ahead and move that over a little bit, 4/3 is the shadow price for constraint 1, and 1/3 is the shadow price for constraint 2. And just to really emphasize this, we know that y1 that's the first solution to the dual, is 4/3, y2 is 1/3. Good. All right. So therefore, I think we have a theorem. What does the theorem say? The theorem says that the shadow price of the ith constraint is the optimal value of the ith dual. The shadow price, should we write that down? The shadow price of the ith constraint, and that is in our max primal, is given by the optimal value of the ith dual, which is yi. Good. And actually the proof was this right here. We just proved it right here for 1. You can see we could do the same thing by proving that for 2. Oh, actually we brought in this little bit too. Good. So these computations that I'm circling here are really nice to be able to reproduce, because they're not hard, but if you think about what they are as you write them, then these theorems make a lot of sense. Okay, so this theorem actually makes a lot of sense in terms of our notation. It just falls out pretty naturally just from the notation that we're using here. Good. All right. So that is our main theorem of 6.8. There is an interesting lemma that the book uses, and let's write it down here. Lemma. This is actually an observation in the book. And what the observation is that suppose that I have a constraint, and I'm going to go ahead and write it in here, a-I-n xn less than or equal to b. Maybe I should take out the lemma for now, bi. And I rewrite that to be ai1 x1 plus ain xn less than or equal to b. Oops, I'm going to run out of space. Boy, it's nice to be able to slide that. bi plus 1. Now, what I'd like for you to do is compare the domain that's defined by this half plane with this half plane. You see that any x value that satisfies the left-hand side automatically satisfies the right-hand side. Therefore, the right-hand side corresponds to a larger domain than the left. And so therefore, what can you say about your shadow price? The shadow price, again, is the price, or is the value by which the z improves when we increase the ith constraint by 1. And so what this is saying, this right here, this observation, is saying that the ith shadow price is always greater than or equal to 0. Right? And so again, let me get out of this red here. This might be hard to see. Let me stick to white. yi is greater than or equal to 0. So again, if you have a less than or equal to constraint, that automatically goes with positive shadow price. And actually, we used this idea when we were actually constructing the dual, but we didn't really say why this works. Okay, and so this is a nice little observation. Again, that was if you have a less than or equal to constraint, the shadow price is always going to be positive or non-negative. Very good. Okay, we're up to time, and so I will probably the next video will be just some computational problems from the homework. Okay, see you later.